Carbon and its compounds. See, this is a very important chapter of 10th class chemistry, which will explain things further down the road. In 11 and 12, this chapter will come in use a lot. That's why it is a very important chapter, carbon and its compounds. Let's talk about carbon. You know you use carbon in each form. Whatever things you use in your life, what is there? Carbon. Let me give you some examples. See, the very first compound, what is this? Sugar. From which thing sugar is made? Sugar is made out of carbon atoms. If I write down the formula of sugar, then that is C6H12O6. When carbon, hydrogen and oxygen add up, then what is made? Sugar. That means sugar is a compound of carbon. See, what is this? Wood. In wood, what is present? Carbon. If there is no carbon, then wood cannot be formed. Right? Wood also contains carbon, hydrogen and oxygen. This one, what is this? Petrol. What is there in petrol? Carbon. In which form? Methane. In the form of CH4. What is present? Carbon. That means if carbon was not there, then petrol was also not present, and if petrol weren't there, then our cars wouldn't have run, isn't it? That means carbon is very important. Then see over here, what is this? These are our clothes. That means what is present in the clothes? In clothes also carbon is present. If carbon wasn't there, then these clothes weren't, and if there weren't clothes, then you would have roamed like this. See here, you would have done that too. What is this? A man. Body. What is present inside our body too? Carbon. That means carbon is very important. Carbon is present everywhere. Sugar contains carbon, wood contains carbon, in petrol, and even in our body there is carbon. Our body is in fact made up of carbon. Our food is made up of carbon. That means carbon is such an element which plays the most important role in our daily life. Carbon is present in everything. So, carbon has a lot of compounds which we use in different forms. Okay, we will deal with all these compounds in this chapter named carbon and its compounds. So first of all, let's see carbon and let's find out what is carbon and what are the properties of it. Okay, so let's see. Carbon, C. What is the symbol of carbon? C. You know this very well. First of all, let's talk about its atomic number. Tell me, what is the atomic number of carbon? Very good. How much? 6. Secondly, we are talking about its electronic configuration. Electronic configuration. You have learned to write its electronic configuration. So tell me, what would be the electronic configuration of carbon? Carbon has 6 electrons inside it as its atomic number. So how many electrons will go in the K shell? 2. And how many will go in L shell? 4. 2 plus 4, how much is it? 6. That means what is the configuration of carbon? 2, 4. You know this very well, that what do we call the outermost shell? We call it valence shell. Valence shell. So how many electrons are there in the carbon's valence shell? 4. Okay. Let's move forward. About valency of carbon. Valency of carbon. This is important. This is so important. See, how many electrons are there in the valence shell of carbon? 4. There are 4 electrons in the valence shell of carbon, and we have studied octet rule, which states that how many electrons should be there in the outermost shell? 8. So are there 8 electrons in the valence shell of carbon? No. So what would carbon do? To complete its octet, carbon would either accept 4 electrons, and what would it make? C4 minus, isn't it? If you give 4 electrons to the carbon, then it would have -4 charge, or it would lose 4 electrons. And for the loss of each electron, 1 plus charge comes. So for losing 4 electrons, what charge would come to carbon? 4 plus charge. So for its own valency, carbon can either accept 4 electrons or can lose 4 electrons. Okay. Now see, there are some problems. Carbon cannot accept 4 electrons at once. And why not? Because the size of carbon is very small. The carbon is very small in size. And if you start pulling in electrons in that, so how much is the repulsion of electrons? Too much, as the size is small and you keep adding electrons after electrons. So how much would be the repulsion between electrons? Too much. And because of this repulsion, carbon would not want to take 4 electrons. That means This process is not possible. Carbon cannot accept 4 electrons at once. Okay. Let's see the second process. Carbon is losing 4 electrons. As I have told you, the size of carbon is very small. It has 4 electrons in its valence shell. And if the size is small, then the attraction force between the nucleus and electrons will be very high, because the distance between the nucleus and the electrons are very less. So because of the small size of carbon, the distance between its nucleus and its electrons, how is that? Very small. So when you extract one electron out from carbon, so see, one electron has been lost. Now the attraction force on the rest of the 3 electrons will get even higher. And if attraction force has been increased, then to extract out electron you will need more energy. If you extract out the second electron, then only 2 electrons will remain. The attraction force on these will be even more. That means as you are extracting out electrons, attraction force is getting higher. That means you won't be able to extract out all 4 electrons from carbon. You will extract one electron and the attraction force will increase. You will extract the second one and the attraction force will increase. You will extract the third one and the attraction force will increase even more. That is why it is also not possible to extract 4 electrons out from carbon. So what is this? Neither we are able to provide carbon with 4 electrons, nor can we take out 4 electrons from carbon. Then how would carbon make bonds? So you have studied a bond. Which bond? Covalent bond. And what is covalent bond? Which is made up by the mutual sharing of 2 electrons. And what do we call these bonds? Covalent bonds. So the carbon we have, what does it do? Carbon shares its 4 electrons with some other elements 4 electrons. Okay. What does carbon do? It shares its own 4 electrons with the 4 electrons of some other elements and make 4 covalent bonds. How many bonds it makes? 4 covalent bonds. See, in this way carbon has completed its octet. Here in the carbon's valence shell, this 2 plus 2, 4, 4 plus 2, 6 and 6 plus 2, 8 electrons are completed. In this manner, carbon does not gain electrons, neither does it loses any electrons. Rather, it shares electrons and by sharing it makes 4 covalent bonds. And as carbon is forming covalent bonds here, how many covalent bonds are being formed? 4. Carbon is forming 4 covalent bonds over here. That's why we say that carbon is tetravalent in nature. We can write this, you have to be careful. Carbon is tetravalent in nature. Why? Because it shares its 4 electrons with other carbon or with some other elements and makes 4 covalent bonds. And that's why carbon is tetravalent. Okay. Apart from this, see, the next property of carbon is very important, which we know by the name of self-combination or catenation. See, I am giving you an example of a compound of carbon which we call C8H18. Okay, its name is octane. We will deal this in this chapter afterwards. This is the main component of petrol. You know petrol? Okay, petrol is made up of this. If I make the structure of this, what happens in this? 8 carbon atoms are connected with each other. 5, 6, 7 and 8. And with each carbon, what is connected? Hydrogen, like this. In this way, hydrogen will keep attached. Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. Right. So what is happening over here? See, carbon, how many carbons are getting attached with each other? How many hydrogens are getting attached with carbon? This is a very important property of carbon. This is the outstanding property of carbon. What does carbon do? Carbon gets attached with other carbon atoms and creates long chains. Like this is a chain. It makes long chains. Any elements, that property in which it makes long chains getting combined with the other atoms of the same kind, what do we call that property? Self-combination or catenation. So we can define catenation as carbon has a unique ability to combine with other carbon atoms to form long chains. See, long chains are formed. Long chains, and this ability of carbon is known as catenation. So carbon getting combined with other atoms of its own kind and making long chains. What do we call this property? Catenation. Catenation. So this was about what is catenation. Now let's talk about why catenation happens. So the next point that we are going to discuss is the cause of catenation. Catenation. This is very important. Catenation is being shown, but why it is showing catenation? See, I have just told you that carbon is very small in size, like this is a carbon atom and this is also a carbon atom. So when carbon atoms will join, what are the sizes? Very small. The sizes of these are very small, so the electrons, those are being shared between two carbon atoms. The nucleus of this carbon and the nucleus of this carbon, both of these will hold those tightly. Let's zoom this picture a bit. See, this is a carbon atom. This is its nucleus. This is another carbon atom and this is its nucleus. When the sharing of electrons will happen in between these two, so I am making electrons in between. Okay. Suppose these are your shared electrons. Right? What does this electron do? It's attracting this nucleus towards itself and also attracting this nucleus. Okay. That means this electron has taken hold of both these two nucleuses. Because of the small size, what is the distance between nucleus and electrons? Small. Here also the distance between the nucleus and electrons are small. So as the size of carbon is very small, so the distance between its nucleus and the shared electrons are very short. So this electron holds these two nucleuses with very tight force, with reasonably strong force. Because of this, the carbon-carbon bond that is formed, how much its bond strength becomes? Very high, very strong bond. So because of the formation of this strong bond, the carbon-carbon bond that is formed, as it is a very strong bond, so carbon keeps adding one after another and through very strong bonds it creates long chains. So the C bond C that is there in carbon, this C bond C which is there, the strength of this is so much. For this reason, what does carbon show? Catenation property. Understood? So we can write this, that why carbon shows catenation. So, due to small size of carbon atoms, covalent bond between two carbon atoms becomes very strong, right? Because electron holds them very tightly. As the nucleus of two carbon atoms hold the shell electron very tightly. So the bond that is being formed is very strong, and that's why a lot of bonds are formed in between carbons. And how much is the strength of all these? Same. That's why carbon shows catenation. And the tendency of carbon of showing catenation is highest. In the period table, the element which shows highest catenation is which one? Carbon. Okay. Aside from carbon, there are some other elements which also show catenation. For example, silicon. Silicon also shows catenation to some extent, but the size of silicon is larger than carbon. So, how much is the strength of this bond? Less. This is a weak bond as compared to carbon-carbon bond. Okay. So carbon-carbon bond is stronger and silicon-silicon bond is weaker. That's why the catenation property of this is how much as compared to carbon? Less. Apart from silicon, nitrogen, phosphorus, sulfur, all these also show catenation to some extent. As if I take the example of phosphorus, then phosphorus exists in this form, in the form of P4, where it makes single bond between two phosphorus. Okay, but it doesn't make long chains like carbon. Why? The reason is same. The size of phosphorus is big as compared to carbon. So how much is the strength of the bond? Less. This is a weak bond as compared to this carbon-carbon bond. So which element has the property of showing highest catenation? Carbon. These were some important properties of the element carbon. Now let's talk about occurrence of carbon in nature. That in nature, in which different forms carbon exists. See, in nature carbon exists in two forms. One is free state and another one is combined state. In nature carbon exists in these two forms. Free state. The meaning of free state is here only and only carbon is present. Apart from carbon, there is no other element present. Example is graphite. In graphite, only which thing is present? Carbon. Second example, diamond. Here also only which element is present? Carbon. Third one is another interesting example, fullerene. We will discuss about this in this chapter later on. You might have not heard about fullerene before, that's why we will not discuss about it here. You have heard about graphite and diamonds. These are the pure forms of carbon. Here only carbon is present, no other element is present. Okay. Secondly, we have combined state. What happens in combined state? Carbon is present or it combines with other elements to form compounds. That means here it is not found in the form of carbon but found in the form of different compounds. And there are a lot of these, such as CO2, carbon dioxide, glucose, C6H12O6, sugar, C12H22O11. This is the formula of what? Of sugar. This is the formula of what? Of glucose. Petrol. What is petrol? C8H18. There are a lot of other examples. Carbonates, calcium carbonate, magnesium carbonate. So carbon gets combined with a lot of elements and in the form of different compounds it may exist in the nature. Okay. So basically carbon exists in two forms. One is free state, which is made up of only which thing? Carbon. Second one is combined state, where carbon gets combined with other elements and make different compounds. Okay. So we are mostly interested in the free state of carbon, and now we are going to discuss that what exactly this graphite, diamond and fullerene are, how they look and what are their properties. Okay. So let's discuss structure of graphite, diamond and fullerene in our next topic, which is called allotropes of carbon. Firstly, let's talk about what are allotropes. See, what are allotropes? Different forms of an element which have different physical appearance and property, which means different forms of the same element whose physical appearances are different and whose physical properties such as mass, size or boiling point, all these are different but their chemical properties are same. So what are allotropes? Different forms of the same element whose physical properties are different but how are their chemical properties? Same. See, to understand allotropes, let me give you a simple example. We have gods, you see, we have different gods in different religion, right? This is Lord Shankar, this is Lord Hanuman, this is Lord Krishna. And who is he? He is Lord Ganesha. See, they are all gods. But are the physical appearances of them same? See, Lord Shankar looks like this, Lord Hanuman looks like this, Lord Krishna is a bit dark, Lord Ganesha has a head of an elephant. How are the physical appearances of them all? Different. How are the physical properties of them all? Different, right? But if we talk about all of them, we worship all of them, the powers of them all are what? Same. That means we can say that the four different pictures that are here, all four of these are the different forms of the same God, whose physical appearances are obviously different, but the rest of the characteristics of them all, how are the rest of the properties? Same. So what these four have become? Four allotropes of God. So what are allotropes? Of the same thing, different forms of the same thing, whose physical appearances and physical properties are what? Different. But the main characteristics of them all, that means the chemical properties are what? Same. What do we call those? Allotropes. So allotropes are different forms of the element which have different physical appearances and properties but their chemical properties are same. As we are talking about carbon, so carbon has three main allotropes which are diamond, graphite and fullerene. See, there are three main allotropes of carbon which we will need to discuss. So first of all, let's start with diamond. See, diamond. Diamond has a very important property which you know very well. That is, it is the hardest natural substance known. Whatever natural substance exists on earth, which one is the hardest of them all? Diamond. See, why diamond is so strong? That can be said by looking at its structure. So let's discuss structure of diamond. Structure of diamond. Before discussing structure of diamonds, firstly that we have already studied, you know very well carbon. Carbon is tetravalent in nature, right? That means how many covalent bonds will it form? 4 covalent bonds. You know this thing? So what happens in diamond? In diamond there are different carbon atoms. Suppose this is a carbon atom. This carbon atom makes 4 covalent bonds with 4 carbon atoms. Okay, and it arranges itself in a tetrahedral geometry. So this is a tetrahedral carbon which has made 4 single covalent bonds with 4 different carbon atoms. Then the second carbon here will do what? It will get attached with 4 different carbon atoms. Then this carbon will be with 4 different carbon atoms, and this carbon will also do the same. Okay, and will get arranged in a tetrahedral manner. Then again the new carbon that you can see, what will this do? It will make 4 bonds and will arrange itself in a tetrahedral form. This carbon will also make 4 bonds. This carbon will also make 4 bonds. Each carbon here will keep making covalent bonds with other carbon atoms. Okay, the number of which will be how many? 4. As you can see, the number of carbon-carbon bonds are increasing. So what happens in this way? Each carbon makes covalent bonds with 4 carbons, and those carbons also make 4 with others. Okay, so what happens in this manner? A very big 3-dimensional network of covalent bonds is generated. 3D networks of strong carbon-carbon covalent bonds. We have already discussed this earlier, that carbon-carbon bond is very strong. So the carbon-carbon bond is very strong. And what has been generated off of this carbon-carbon bonds? A very big 3-dimensional network. So due to the generation of this 3-dimensional network, the diamond becomes very hard and brittle also. Okay. Due to this very big network of covalent bonds, how is diamond? Very hard and brittle. And for the same reason, we say that diamond is the hardest natural substance known on the Earth's surface. Let's see the structure of this a bit in detail. So see, as I have told you, each carbon is attached with 4 carbons in tetrahedral manner. That carbon is arranged with some other carbons with some other 4 carbons in tetrahedral fashion. Each carbon is attached with 4 carbons in this way, and a 3-dimensional network is generated in this manner of carbon-carbon covalent bonds. And that is what? So much strong. This is still a small network. This network grows even more. So let me show you another picture through which you would have a clearer idea about how this network actually looks after the formation. See, this one. This is also the structure of diamond. How many carbon-carbon bonds are there? You can't even count how many carbon-carbon bonds have been generated. Each one is strong bond. Here, so much bonds have formed. That's why diamond is what? It is very hard, and it is the hardest natural substance. See, I am using a term repeatedly, hardest natural substance. Natural substance because there are some man-made substances too which are even harder than diamonds. And one example of that is tungsten carbide. Okay, you don't have to remember this. I'm just telling you this for your GK, for general knowledge. What is even harder than diamond? Tungsten carbide. That is why I'm mentioning natural substance repeatedly. So this is the story of the structure of diamond. In the structure of diamond, we have learned that carbon atoms are bonded with 4 other carbon atoms. That means how much is the valency of carbon here? Complete. Valency of carbon is complete. That means all 4 electrons of this have been in use in sharing. Are you getting it? So I would use this tip later on. So that's why I'm defining it here, that inside diamond all the 4 electrons of carbon get used. So let's discuss the properties of diamond. So the very first property of diamond is, due to presence of large 3-dimensional network of covalent bonds, that is carbon-carbon covalent bonds, diamond is very hard and has high melting point, which is around what? 4827 degrees Celsius. Due to the big network of these carbon-carbon bonds, diamond becomes what? It becomes very tough, very strong, and similarly its melting point becomes what? Very high. See how high it is, around 4827 degrees Celsius. The second property of diamond is it is a bad conductor of electricity. Right. What is this? This cannot conduct electricity. And why not? I have just told you that, see, carbon inside diamond is attached with other carbons with 4 covalent bonds. Where do the 4 electrons of carbon get in use? In sharing. To conduct electricity, free electrons are needed. What are needed? Free electrons. Right? You tell me if carbon has any free electrons left in diamond. No, this carbon will make 4 bonds. This will also, and this will too, and this will also make 4 bonds. That means carbon is utilizing its 4 electrons in making bonds. So it has no free electrons left. Right? That's why diamond is what? It is a bad conductor of electricity. So we can simply explain that the 4 electrons have come in use of bonding. Therefore, there are no free electrons. So if there are no electrons, then diamond cannot conduct electricity. Right. It is a bad conductor of electricity. The next property of diamond, you know this very well too, that is, it shines in presence of light. Whenever you drop light in diamond, so what does it do? It shines. See, what is its reason? As light comes and drops into diamond, then that will enter through this face, and after entering, light will start to do what? It will start to reflect in these faces, in this manner. After reflecting, what would it do? It would get trapped inside diamond. See, what are the angles of the faces? These are all different. So as soon any light ray enters diamond and incidents on this, and after going inside its faces, what does it become? It gets trapped. So that's why in the presence of light, or whenever light drops in diamond, what does it do? It shines. We can simply say that as light ray falls on diamond, it gets trapped in its interior faces, and due to that, what happens to diamond? In the presence of light, diamond shines. And for the same reason, it is transparent, right? How are diamonds? Diamonds are transparent. Why? Because whatever light falls here gets trapped inside. And secondly, how diamonds generally are? Colorless. So diamond is transparent, colorless, and has a brilliant shine in presence of light due to their specific structure.